everyone. This is Poornima Deepthi, working as an assistant professor in the Department of ECE at MLR Institute of Technology. Today's video is about how we are writing programs using 8051 microcontroller. So, the overview of today's presentation is how we can exchange the data from internal memory to external memory, or how we can duplicate the data. So how we can perform subtraction, division and data transfer between the controller and other devices. So coming to the first program, here the program is about how we are exchanging the data from one memory location to the other memory locations. As you can see here that the data, the address they have mentioned in the program statements itself is one is 8-bit address location and another one is 16-bit address location. So here itself we can identify that this is the internal memory location and this is the external memory location, right? Where the internal memory location of 8051 is 128 RAM size, 125 kilobytes. So here FF is representing the internal data, internal memory, and 16-bit data. So here 16-bit address represents it is a external. So the data present in the internal FF location need to be exchanged with the data present in the external location FF00. Let us consider the data present in FF location is 1, 2. 1, 2, and the data present in FF00 location is 3, 4. So now after executing this program, our motive is that the data 34 need to be moved to the FF location and the data present in FF location need to be moved to the external memory location. Let us see whether we can interchange or exchange that thing, right? The first one is, so we need to access the data present in the external location, right? So how we will access the data present in one particular address location, so that if we need to access the external memory or external data, so in 8051 we can use only one and only register to access the external, which is nothing but DPTR, data pointer. So here DPTR, data pointer, is a 16-bit register. So which is used to access the external data. So that's why the external memory which they gave has been loaded into the DPTR. We are moving that data to address to the DPTR. But here one thing is there, before using the direct memory address FF00, why we are using 0 over here? So if we are representing the hexadecimal numbers, the hexadecimal numbers from 0 to 9 are equivalent to the decimal numbers, but after that we are mentioning it as A, B, C, D, E and F, right, from 10 to 15. So here in this particular case of alphabets which we are using as a hexadecimal numbers, so we can't represent alphabets right directly in the first position. So we need to mark up by using 0 before that. But there 0 doesn't represent anything, but you need to represent 0 before that, that the controller can access it as a hexadecimal number. That's why I kept 0 between before FF. If we didn't mention 0, it will throw some error. Okay? Yeah. Next, coming to the next thing here, the next instruction. So after executing this first instruction, we are having the data in the DPTR. DPTR consists of FF00 address. Now after execution of second instruction, what is the second instruction? Move X. Why we are representing X over there? The remaining instructions doesn't have X, but this particular instruction and the last instruction is having. So why we are keeping move X means, so when we are accessing the data from the external memory, then you need to represent move X so that the data can be getting from the external memory. Okay? Yeah. Here the data present in the DPTR. Here I am indirectly mentioning the content of the data present in the DPTR. So the DPTR consists of FF00, but I need to access the content of FF0. That's why here I have been using @. So @ is indirectly mentioning the data of that particular address. So here the DPTR is having one address. The data present in that address should be moved to the A register. So here the data present in FF00. What is the data present in FF0034? So after execution of this second instruction, what is the value present in A? A is loaded with 34 data. Right? Yeah. Now we need to keep this 34 data in the location of FF. Right? But before placing the data in the FF location, I need to preserve the data present in the FF location into some register. So before losing that. So that's why I am mentioning that @FF means the data present in the FF location is, what is the data present in the FF location? So it is 12. So 12 will be loaded to the, so here no need to write @. So FF location, so the data present in FF location is 12. That 12 is loaded into the R0 register. R0 now is having the data 1, 2. Now we are having two contents in two registers. So now we can just copy the contents into the required address location. So now the data in next, the data present in A. What is the data present in A? 34. Need to be moved to the location FFH. So FFH before it is having 12 will be get cancelled and the data it is loaded is 34. So after execution, the FF location is having the data 34. Half of the program is done. So next what we need to do? We need to keep the data before in the FFH to the FF00H. So now the R0 is having 12. This need to be moved to the accumulator. Why can't we just transmit the data directly to the DPTR locations, external locations? No. If you want to transmit the data from one internal memory to another external memory, then you need to access by using only accumulator. Accumulator is a special register that carries the information interchange between the internal RAM and external memory locations. That's why here we can't directly write move x @DPTR R0. No, because R0 is the internal RAM register and DPTR is the external register. So we can't exchange the information between these two directly. That's why we are using accumulator over here. So the data present in the R0 need to be copied to the accumulator. So after execution of this instruction, the accumulator is loaded with 12. This 12 need to be moved to the location of FF00. So that's why here I am mentioning DPTR, because here in the DPTR we are having FF00. I need to place the content into the location of FF00. That's why I am using @ symbol over here. So the content of FF00 will be loaded with the content of A, which is nothing but 12. So here 34 will be replaced with the data 12. So this is how we will perform the exchange operation between two locations, which is one of the internal to the external. Right? Yeah. Coming to the next program. So here it is the duplicate. How we can duplicate the data? See, the statement is I need to store the higher nibble of R7. Let us consider that R7 register is holding the data 1, 2. Okay? Yeah. So this higher nibble, which is higher means this, higher nibble is this and lower nibble is this. Nibble is nothing but 4 bits of data. These hexadecimal numbers can be represented as 4 bits each. And this need to be stored in which one? Into both nibbles of R7. So R7 need to fill with the higher nibble of R7. R6 need to be filled with. So the contents after executing the program is R6 register need to have the data R11. So here R6 register need to have data 11. So how we will perform this? Let us see. So what is the data I need to? So R7 is having the data 1, 2, right? So we need to focus on the higher nibble only. Here we are dealing only with the higher nibble. So how to, so I need only higher nibble. So how I can eliminate the lower nibble? So there is one logical operation to eliminate the unwanted nibble. So which is nothing but ANL. Performing AND operation between the contents of A register and the location of F0H. Okay, and the data with F0. Here it is not location. Here we are mentioning hash, means we are performing AND operation between the data present in the A register with 0F0. So how we will perform the operation? Let's see. So the data present in R7 is 1, 2, right? So we need to convert it into, to perform AND operation, to be able to understand, I was converting it into the binary format. Okay. So the data present in R7, consider. So 1, 2. So we need to convert it into the binary. So 1 is converted into 0001 and 2 can be converted into 0010. Now I need to perform AND operation. So that I need to eliminate this lower nibble, right? So how to eliminate this lower nibble? If you want to eliminate the data, so you can perform AND operation between 0 and the actual data, so that the data will be vanished. Let's see how. Here we need to perform F0. So what is the value of F over here? So F is nothing but 16, right? Yeah, 15. So 1, 1, 1, 1, all ones. So now 0. So 0 can be 0, 0, 0. So I need to perform AND operation. What is the logic of AND operation? If both the inputs is high, then only we will get the output as high. Here, no, 0, 0, 0, 0. Here 1, 1. So here we will get 1. The remaining else is 0. So what is the value over here? 1 and here 0. Now I have eliminated the lower nibble, which is not important for this case, right? So what is the data after this performance of this instruction? The output after execution of first instruction, the accumulator is having the data 1, 2, right? Which is R7. R7 is having 1, 2. So that's why accumulator is also having 1, 2. So now we are performing AND operation between accumulator and F0. So what will be the output after execution of this instruction? So the accumulator A is having the data 1, 0, right? Yes. So now this move R1. So what is the actual output we needed? So R6 need to have 1, 1 over here. That's why we are having 1 in the higher nibble. So we are moving this to the R6. So after execution of this instruction, what is the data present in R6? 1, 0. Okay. The higher nibble is having 1, but we need to have the lower nibble also 1. So what we need to do? So first we are swapping the nibbles of A. So what is the swap instruction here? The swap instruction performs the exchange operation between the two nibbles in the register. So A is having the data 1, 0, right? Now it will exchange this lower nibble as higher nibble and higher nibble as lower nibble. So after performing this instruction, the data present in A is 0 and 1. Now, so I need to place this 1 in the lower byte of R6, right? So how we will perform? So just we need to perform OR operation between these two numbers. So what is the data present in A? So the data present in A is 0, 1, which is nothing but 0, 0, 0, 0 and 0, 0, 0, 1. And the data present in R6, what is R6 data? 1, 0. So 1, 0 can be 0, 0, 0, 1, 0, 0, 0, 0. So here to perform, to get this 1, 1 value in R6, we are performing OR operation. What is the logic of OR operation? If any one of the input is high, output will be high. See, 1, 0. So here 1. So remaining ones. Here also 0, 1, 1. So what is the data present in R6? 1, actual hexadecimal number. 1 and 1. So that's what we require, right? So the data present in here, accumulator is 1, 1, that need to be moved to copy to the R6. So here we are writing move R6 comma. Here A equals to 1, 1. Now we need to send this, we need to copy this into the R6 register. So R6 register after execution will be copied to 1, 1. This is how we will transmit the higher nibble of R7 into both nibbles of R6, right? Yeah. Coming to the next program, here in the statement itself, they mention that feed R6 and R7 and R4, R5 as two 16-bit registers. Perform subtraction between them. So we need to perform subtraction between these two 16-bit data present in two different registers. Store the result in 20H. Lower byte should be stored in 20H memory location and higher byte should be stored in 21H memory location. So let us consider that R6 combination with R7 is a 16-bit data. So just holding as 41. Just consider it. Right? Yeah. So R6 is holding the highest byte and R7 is holding the lowest byte. So we're in the combination of R4 and R5 also. So the R4, consider it as 82, 84. Okay. So R4 is holding the highest byte and R5 is holding the lowest byte. Right? Yeah. So now we need to perform. So before performing the subtraction operation, we need to make sure that carry flag should be 0. Why? Because here in the subtraction, we are doing subtraction operation by using the borrow. So borrow means if carry flag is having 1, that 1 should be subtracted from the register itself. So that's why we need to make sure that carry signal should be 0 before performing the subtraction operation. That's why here in the case we are clearing the carry. So the carry is 0. CLR means clear. So carry flag is 0. Now we are moving the highest byte of R4, highest byte of the number. So what is the data present in R4 here? 82. So A will be having 82 after performing the execution of this instruction. Now we need to subtract the data 82. 41 will be subtracted from the 82. So that's why here R6, the data present in R6 is 41, need to be subtracted from. So here A minus R6, the data present in A is 82 and minus the data present in R6 is 41. So the highest nibble will be subtracted, highest byte will be subtracted and the output will be stored in which one? A register. So now we need to move this A, so lower byte to the A register. So here this is 21H and this is 0. So here the output A 21H, higher byte need to be moved to the 21H. So that's why we are moving A, the output of higher byte to the A to the 21H address location. Now we need to perform the same operation between the lower bytes. So here I was taking R5 as the lower byte. So R5 minus R7 should be done. So first I was moving the data in the R5 register to A. So A is having the data 84 and the data 21 should be subtracted from this. So that's why A minus R7. So 84 minus 21 will be performed over here and the output will be stored in A register. And we have mentioned that the lower byte of operation should be loaded into the 20H. So the 20H memory will be loaded the lower byte operation. This is how we will perform the subtraction operation by considering 16-bit subtraction operation by combination of two registers of 8051 because each register of 8051 is only of 8-bit register. So coming to the next one. So how we perform division operation? Here it is not a simple division operation. There is one condition that we need to check over here. The statement is having divide the content of R0 by R1. So the operation should be done like this, R0 by R1. Right? If we consider the data present in R0 is it is 12. Suppose it is 12. And the content present in the R1 is 4. So, while doing the division operation, we are having two outputs, right? One is coefficient and another one is remainder. We need to take consideration of these two both, right? So, next one, store the result in R2. Answer means quotient and R3, remainder. So, R2 need to be have coefficient and R3 need to have as a remainder. Then restore the original content of R0. So suppose if we are taking R0 as dividend, right? So we need to find out the dividend. So what is the formula or how we can find out the dividend actually? So the dividend is equals to coefficient into divisor and plus reminder, right? So we need to follow this formula to find the part over here to restore the original content of R0. So we will see how we are doing this, right? By using programming. The first one is we need to perform division operation. So let us consider R0 is having just 12 over here and R1 is having 4, right? Yeah. So move R0 to A. So after performing, we are having the dividend into A, right? And move B R1. So we are having the divisor over B, 4. So now div AB is the instruction to perform operation of, so the dividend by divisor. So 12 by 4. Actually we will not get the 3. Are we getting the 3 over here? So let us check. That one is the hexadecimal number. So 1, 2 means 16 plus 2, 18. So 18 divided by 4. What we will get? So 4 as the coefficient and the remainder is 2. So we will check whether we are getting that or not. Now, yeah, we actually perform the operation, and in multiplication and division operations, the coefficient in division, particularly in division, the actual answer, which is the quotient, will be stored in R2 A register and the remainder will be storing in the B register. That's why here directly we are taking. So they mentioned that R2 need to have actual answer, which is quotient. So A is having the quotient and B will hold the remainder that need to be moved to R3 as they mentioned. So here R2 is having the quotient and R3 is having the remainder. Until here we have done. Now we need to take the consideration that then restore the original content of R0. What they mentioned, so we are taking R0 as the dividend. So how we will find out the dividend? So we are having coefficient into divisor plus remainder. So first we need to multiply the coefficient and divisor. So here we know that R1. So where is R1? R1 is having the divisor. So we need to multiply divisor with the quotient. So here quotient, where quotient? R2. So that's why first we are moving it to the back. So R1 is moved to B. So what is the value of R1 here? R1 is having divisor. So here B is having the divisor. And actually we know that A is having the quotient, right? So multiplication. So coefficient into divisor is done over here. So we need to add remainder over this. So just add A comma R3. So R3 is having remainder, right? So coefficient into divisor plus remainder, which gives us the dividend. So this will be stored, and they mentioned that the dividend should be in the R0. That's where we are moving accumulator. So the data present in the accumulator is the dividend. So that we are moving to the R0 register, right? Yes. So coming to the next program. So here it is a data transfer just, but the thing is here the block of data. So you can call it as an array, a block of data which is nothing but array, and they have specifically mentioned the locations, and this internal block of data should be moved to the external locations. In the first program we have discussed how the one content of internal memory will be loaded to the other content of external memory, but here one block like array. So such type of we need to run it as in the loop. So how we will write loop in programming of 8051? So consider this. So first we need to transfer the data of how many? 20 to 29 means 10, right? So consider 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So how many locations are there? 1, 2, 3, 4. So 10 locations. So 10 bytes of data should be moved to the 10 bytes of external locations, right? So 1020, 1021, 1022, 1023, 1024, 1025, 1026, 1027, 1028 and 1029. So I need to move the data present in 20 to 1020, 21 to 1021, like that. So how we will perform this operation? Let's see. So first of all, we need to transfer how many blocks of data? So 10 blocks, so 10 bytes of data. So that's why I'm keeping count of 10 in the R7 register. 0A means A in the hexadecimal represent 10, right? So A is having decimal 10. It is a loop or count. We are keeping it as a count. Now, move R0, 20H. So we are moving the address of 20H to R0. So R0 is having 20, which is the internal address location. And we are moving the external memory location. As in the first program, I have already explained why we are taking DPTR. DPTR is a data pointer which is of a 16-bit address location of external memory. So that's why external memory, they mentioned it as a 1020. That's why we are moving DPTR is holding the data of address 1020. Now, the data present in R0 should be moved to the accumulator to transferring the data. So here, after performing this instruction, A is having R0. What is the R0 value? 20. So the contents from the 20 should be moved to the accumulator. What is the contents from 20? Let us consider 1, 2, 3, 4. For just examples, I was taking this. So here we are having 11 data that should be moved to the 1020 location. So this first 11 will be moved to the accumulator 11. So from accumulator, we need to transmit the data to the DPTR. What is the data present in DPTR? 1020. So the 1020 location will move having the data 11. After execution, the 1020 is having the data 11. So first byte has been transmitted. Now we need to perform this 9 more times to transmit over the 10 bytes. So I can keep one loop. So it will repeat until the 10 bytes has been over. So how? So next what we are doing? Incrementing R0. So we are having R0 as 20. So after incrementing, what we will have? R0 value 2, 1. And here incrementing DPTR. Here we also incrementing DPTR. So what we will do? The DPTR value 1020 is incremented to 1021. So the DPTR value is having 1021. R0 is 21. So now the data from here need to copy to or copy to the 1021 location. But here 1 byte operation already done. So what we need to do? First we need to decrement the loop. So first we need to decrement the count. Where we kept count? Count is set in the R7 register 10 bytes. So 1 byte already been copied. So we need to decrement the count. So here one instruction, that is decrement, D, J, and Z. Decrement and jump if no 0. After decrementing, if the value is not 0, then only loop will be performed. Okay. So R7 is having 10. So after decrementing, what it will become? 9. So it is not 0. So the loop will be executed. So what is the loop that need to execute? Next. So here we gave next operation. So again from here the operation will continue. Now the data is loaded from 21. R0 is 21. So what is the value in 21? 21 is 21. So this will be moved to this location. Again the same operation. R0 will be incremented to next location 22, and here also 1020 location will get, and again decrement operation will be performed. R7, now R7 is having 9, so it will become 8. So it is not 0. Again the loop will execute until when? So it will be, if it is having 0, after decrementing 10 bytes has been transmitted. Now what it will do? Decrement jump if not 0, but 0 is there. So the next instruction will be executed. If we kept as halt, so the program end there itself. Okay. This is how we will transmit the block of data from internal locations to the external locations. Yes. So until now, we have discussed how to transmit, how to exchange the data present in the internal location to the external location, how we will perform the subtraction operation, how we will restore the division operation, and how we will performing 16-bit subtraction operations. So by using only 8-bit registers, and how we will calculate the dividend by using the programming of 8051 microcontroller. So, thank you.